Okay, now if you do the calculations and do the graphs and reason it out, we find that the acceleration here would be 27 centimeters per second squared. Here it would be 60 centimeters per second squared. Here it was 12 centimeters per second squared. I'm going to put that on this green graph here. Remember that previously I said that we've labeled the ramp slope, and we've got points representing 1 over 60, 2.5 over 60, and 5 over 60 on the horizontal axis. And they're relatively to scale. I think the 5 should have been out just a little further, but that's okay. And our numbers then are 12, 27, and 60 for the acceleration in units of centimeters per second squared. That gives us 3 points on this graph. Okay? And those 3 points, if you plot them, come reasonably close to a straight line. Okay? Some of them are a little above, some of them might be a little below the best possible straight line. But they all come pretty close to a straight line. The way I've graphed it here, and I wasn't fudging the graph, actually I miscalculated this one, had this point way up here, so that this point was higher and the graph had a curvature, and it wasn't particularly linear. When I fixed this, that point went lower, and by darn if they didn't line up quite well. Now this is a hand sketch graph. If you draw it carefully on graph paper and so forth, you'll see that they very unlikely that they lie on a really, that all of them lie really close to the same straight line, but I think they'll be pretty close. Now this is an experiment that we're going to do Friday, so you have to understand all of this analysis, because I don't want you doing it just by plugging into formulas. I want you doing it with understanding, comprehension, with a deeper understanding based on understanding of this graph. What's a rise mean? What's a run mean? How's that related to acceleration? Or how's the area related to displacement? Okay, you need to be able to do that sort of thinking. Hopefully you develop that thinking in a calculus class, but often it's, again, you get lost in the details and forget the big picture. So, big picture. Slope is a rise divided by a run, and that represents something depending on what your graph is. If it's a V versus T graph, then the rise represents change in V, the run represents change in T, so the slope represents change in V divided by change in T, or an average acceleration. And area is average value times the interval, and that's what your integral tells you. If you have a straight line graph, those average values are very easy to see, very easy to work with. If you don't have a straight line graph, well, then you do have to do a little bit of calculus if you want to get average, if you want to get accurate results. For what we're doing this week, except for a few problems that are really actually fairly easy, people seem to be doing well with them. There are a few problems where you got to use calculus. People are doing okay with that. But for the uniform acceleration, which is really the mathematically simpler, in a sense, things are, as expected, a little bit shaky. So you want to have that down by Friday. You don't want to be stumbling over that while you're thinking about what's going on these ramps.